Audio check, mic check, testing 1 2 3. Mic check, testing 1 2 3. Audio check, mic check, testing 1 2 3. Mic check, testing 1 2 3. Okay, so this audio seems to be alright, and we are live. Hello and welcome back to another day of working out some physics problems. Today we're actually diving a little bit more. It's definitely still physics related, but it comes more from the background of materials science and thermodynamics. So one problem that I had seen in one of the lectures that I saw was the derivation of basically entropy and going about it. We're gonna make a few assumptions here and use what's known as a Boltzmann distribution. So the Boltzmann distribution basically says that when you're comparing the probability of two events, the probability of, say, event A happening is proportional to some type of constant times an exponential, and you have negative exponential to the negative, and then some type of energy for that event to occur over kt, or k is Boltzmann's constant. And same thing with the probability of B. And so if you wanted to see basically the ratio of what would happen with these two, you basically would divide them. So if I wanted to see what's the probability of event B occurring compared to event A, you'd basically get this. The C's would end up canceling out, and you have this. Okay, and this would end up being equal to, well, we could just leave it at that for now. And the reason why we care about this is because we want to look at a model system where, say, we have n atoms in our system, right? In this case, I'm just going to drop 16. And say, I have a selection right here. I'm not sure if I could select all of this, and that's fine. What we want to do is basically compare lasso. Yes, I think this is what I want. Boom, boom. Yes, okay, great. Okay. We want to compare these two systems. So a normal system like this is actually going to have some energy to it. Right? It's going to have an energy to it. We'll just call it epsilon naught for now. And this system right here, we could just probably add the atom here, and we could just say this is infinitely large. If we had really, really large n, so we wouldn't really be able to tell this. We still have the same number of atoms here. We just have one displaced. So we have one that's out. So we have what's known as a vacancy. It's missing from here. So normally there would be an atom here, but we don't have it anymore. So this actually introduces what's known as a defect formation, a vacancy formation. And this actually increases the energy of the system. And so we'll denote this by an additional energy, EF. Okay. And what's interesting is we want to see what's the energy difference of these two systems. Well, when we end up looking at it, it's basically just this equation, right? Where we look at the energy of one system. So this is the energy of the pristine, and this is going to be the energy with a defect. And so when we end up looking at what would be the probability of a defect in probability of D with defect versus probability of having a pristine system, we end up finding out that we have this exponential minus, and the difference between these two is just going to be this over kt. And so one might look at this and think, okay, well, this is basically going to be a ratio of how many defects you're going to have in a whole entire crystal. And so just numbers to play around with. The approximate value for vacancy defect formation for some metals is about it's about 1 eV, which is an electron volt. And for KT at room temperature, so approximately 300 Kelvin, KT is actually equal to 0.025 eV. And so if we were actually to look at this ratio, we have an exponential minus, we have 1 eV over 0.025 eV, which gives us about e to the minus 40. So I don't know about you guys, but this ratio is very, very, very small. Let's use our handy dandy Wolf RAM Alpha calculator and figure out what this is approximately. So exponential minus 40 is about 4 times 10 to the negative 8. This number is very, very small. But we actually see a good portion of particles of defects. Defects occur. So this number, even though this number is very, very tiny, defects do occur to a large extent. And this basically would tell us that they really wouldn't happen. That there'd be like one defect or a couple thousand in a mole, which is a crazy difference. When you look at what a mole is approximately 6 times 10 to the 23. But we're talking about a lot more defects occurring in systems. And so where the neat part of this is the probability of this occurring happens for this particular microstate of and so what we need to account for is that there's, rather than just this case happening, we could also have this case where we'll have, rather than this one being the chosen one, we have this one, right? And we could also have the case where it's this one's chosen, this one's chosen, this one's chosen, this one's chosen. So this probability is only for this specific case. The problem is we can have many different cases happen. And so that's where the challenge comes from, where the probability of us just having one defect in the system is actually this number times the number of possibilities. And so now, as we start looking at this, we start realizing that having just one defect in the system is not just this probability. It's this probability times n, right? Should be n times 4 times 10 to the negative 18. So if we have a larger number for n, this number starts increasing. But when we talk about two defects, now we have to talk about n times n minus 1 divided by 2, so we don't so we count for them appropriately, and then we'd actually double this because there's two defects in the system now, right? So e to the 2ef and even though this probability is a lot less likely to happen. So if we were to calculate this, basically we'd have e to the minus 80. Let's see how much more unlikely this would be. We'd see it's 1 to the 10 to the 25th probability. So it's even less likely for this to happen in our system, right? It's about 2 times 10 to the negative 35. So it's even less unlikely to happen. But remember, so now we're multiplying this by n. And so what's interesting is when we start looking at it in this light, we realize that there's a lot more chances of us having a defect because there's more microstates. And so there's actually going to be a balance between having a lot of having a certain amount of defects and then having the number of defects occur. And so when we actually want to calculate the probability of having little n defects given big N number of atoms in our system, then the probability of this occurring for one microstate is going to be the energy of the regular system, NEF, over K Boltzmann constant T times n factorial over little n factorial. Oops. It's actually big N minus little n factorial times, oh yeah, n factorial. That is what I had. Okay. Just want to verify something real quick. It might be an actual error on the professor's part. I'm not sure if this part should be here. Because if we were to try to take the ratio of this, oh no, I guess technically we're just calculating for one of these parts. And then this could then be taken out later on because this is for one part. Okay, yeah, so this is correct. Yeah, so the value is going to be approximately this. The problem is where you see we have little n here, little n here, little n here. And so we want to find out approximately what's the optimum n to have such that we balance increasing the energy of the system, but at the same time increasing the maximum amount of possibilities for these defects. So even though the energy is going to be increasing of the system, because there's more possibilities of this happening, that state would most likely be there would be a more likely state for there to be n amount of defects. And so one way to calculate this when you have something really interesting like this is to actually take the logarithm of both sides. And so that'll actually help us simplify this. So if we were to have our new function, so we'll say a new function f and this is actually going to be the logarithm of this. Is equal to, we're going to have log, so I write log, but it's the same as ln in this case, where we're actually referring to the natural log. So we're actually going to just take this part out because it's constant. And we're gonna do this over kt times n factorial. And so this is a combinatorics response. If there's a lot of questions on this, maybe I can make a video on it later, going more in depth. Okay. And so in working this out, because this is a logarithm, the natural log of an exponential just gives us this out, which is equal to minus n ef kt, and then plus the log of all this, n factorial over n minus n factorial n factorial. And so we could expand this further actually, because remember the properties of logs, if you're multiplying anything, you could just add them. If you're dividing by anything, you just minus them. So this is going to be equal to discontinued plus the log of n factorial minus log n minus n factorial. So it's the inside, this is minus the factorial part, log n factorial. And so here, this would be very difficult to do. And so what we're gonna approximate in the limit, we're gonna assume that this n, the number of atoms we're dealing with, and usually we're dealing with like Avogadro's number, is way bigger than say the number of defects. But this number of defects is we're also gonna approximate is bigger than 1. And so given this, we can actually use Stirling's approximation, which Stirling's approximation is that if you have a very large number, say log of a factorial, assuming a is very large, then the approximation is that you end up getting a log, again this is natural log, a minus a. So this is the approximation. We can probably do a few examples of this and actually see what that's true using Wolfram. So if we assume something very large, ln of 10 to the 23rd, and we'll actually, what is this value? It's about 52, okay? 53. And so if we were to subtract it, our Stirling's approximation, we would say that this is, so what does this be? Boom. Times ln of 10 to the 23rd minus 10 to the 23rd. What is this equal to? This seems very wrong. Oops. Oh, that's what we were missing. It's supposed to be factorial. No wonder. I don't think Wolfram will give us a value. This number might be too large. Oh, result. Oh, okay, yeah, this is cool. Okay, so 5.2 times 10 to the 24. Okay. And then if we were to then do this is Stirling's approximation. So 5.2 times 10 to the 23rd Oh wow, it's about 5.2 times 10 to the 24. It's the same, almost same value. Neato. This is pretty cool. I didn't know that. How good of an approximation it would be. I guess when it comes to large numbers, that would make sense. I guess let's subtract the numbers very briefly and see how off we are. So this is pretty funny. We're still off Sterling's approximation. We're only off by about a billion. But when we're talking about numbers, say 10 to the 23rd, you don't understand the magnitude of this is incredibly large. So if we're thinking in terms of a percentage, of how much we're off, that would be 10 to the negative 14 approximately. That's like 1% of 1% of 1% of 1% of 1% of 1%. Maybe a lot more. So it's a very, very great approximation, at least when we're talking about percentage wise. Okay, so the Sterling's approximation, let's go for the win. And in using that, we make, oh, this should be an approximation. So it's not exact. And that's fine. So when we expand that, we still have our value here, n times the energy over kT plus n log n minus n, because remember that's the first term, and then we have minus n minus n log n minus n. Then we have, oh, this is interesting right here. We had to put this in parentheses. N minus n, and then we also have for this term n log n minus n. And so what we could see in this term, we have minus minus n, which is a plus n. So this term will cancel with this term. And then we have minus minus a minus, so this is negative n. And we have minus minus, this is positive n, so these terms cancel. And so what we're left with is this plus n log n minus n minus n log n minus n minus n log n. Okay. So let me see something real quick. Yep. And so this is what we have, right? And so this is our function. And so what we want to do is we actually want to find out when is this function largest, right? We want to find out which one has the largest probability for n. And what's interesting is that this is if you take the logarithm of a function and it has a maximum, the maximum of the log position is still going to be the maximum of this position. So we want to find out the maximum of this one. And we can do that by taking the derivative with respect to n and setting it equal to 0. And so we take the derivative of this with respect to n, we get EF, because this is just n times a constant, KT. This is a constant, so this goes away. We're actually going to do a little chain rule on this, I believe. And that will give us, we take the derivative of this. So we'll be left with n, oh, nope. We should be left with a minus 1 because derivative of this times this. And then we take the derivative of this with respect to n. And so we get this part. The derivative of log is 1 over that factor. But so we will have n minus n, but we get a minus 1 because you have to, I guess, do chain rule inside of here, and you get the derivative of minus n with respect to n is equal to minus 1. And so we do the same thing here. Take the derivative, we get log n. And then when you take the derivative of the inside here, we get n over n, which is just 1. Okay. So let me see if I did this correct. So this actually should have just been a plus, because I am assuming I'm just doing it here and I left that minus outside to then distribute later. And what does this equal? Okay. We're left with EF KT. We're having a little technical issues, but we're back at it. So we get plus 1 here, so plus log. Yeah, I think we might be having some connection issues. I hope this is still recording well. And then we distribute this one over here. This would cancel with that. This over this gives us then plus 1. And then when we look at this, we get minus log n. And this minus distributes here to get minus 1. So let's see if I did this right. And this is going to be equal to, we continue writing this part, plus it's going to be this over this. Did I do this right? At least from what is written in the notes, we're off by something. Oh, my apologies. This should be log. Okay, I might have messed something up. We might be off by a factor of 1 somewhere. So I know up to this point, our equation's fine. It's somewhere here. Okay, so this term drops off because it's not dependent on n. When we take the derivative of this with respect to n, we get minus 1. Log this. That's fine. And then we get this here. Take the derivative with respect to n, little n here. You drop this whole thing down, you get minus 1, that's fine. And then when we jump to this part, what do we get? We get log n, yes. this, this. Yeah, I don't know if my professor made an error on this. Because this is what we got. This is equal to 0. What he got was this. I don't know if he made an approximation where n minus little n is just equal to big N. It's possible because remember we made this assumption bigger than n. And it might be fine. So this is what they got. This is what we got. I think for now we might go with their approximation because it would actually make looking at some of this stuff easier. And so when we look at this, we can subtract over to the other side. We're left with log n over n is equal to minus EF over KT. And when we take the logarithm, both sides, let me see what they do here. Oh, nope, this should be plus. Because we moved it over to the other side. We could actually flip this though, and then it does become minus again. You could extract a -1 out of that. And then you could take the exponential of both sides. And this will just give you little n, big N is equal to the exponential minus EF over KT. And so this is actually, okay, so let's figure out what is this? Oh, yeah, this is actually the value we're gonna want to plug in for this, right? So let me see. Okay, yeah. So what we basically solved for is this is the ratio that would give us the most probability in our system. We choose an n value, little n value, such that when little n over big N is equal to this, or at least close to this is our maximal value, right? And so let's see what happens when, okay. This is really interesting. One thing then we went into along with this. So okay, so let's just take a moment right here to just stop and see this. Basically, little n is equal to this. And so let's say if we use Avogadro's number and we use the same values as before. So for our system, we have 10 to the 23rd atoms. And so if we're looking at the number of defects, say vacancy defects, 10 to the 23rd, this big N, times this E to the, say minus this. So we already calculated this, right? This was 1 EV over, for our room temperature, over this. What did we say this value was? E to the 40 was 4 times 10 to the negative 18. And what value is this? This is going to be 4 times 10 to the 5. 10,000. So in here, basically we will have, you're very likely if you have, say, near like 1/6 of a mole, I guess, of your system, you should have 10 to the 4 times 10 to the 5 defects in your system. Or approximately that's the most likely scenario, because remember, this is still a particular set of that's just what your probability distribution looks like. So it's probably really low, it increases, and then it probably decreases. And so here you have 10 to the 5th defects. And so what's really interesting is there was a highlight that the professor had really had demonstrated, is that if we look at the free energy of a system, this is equal to the energy of the system minus something that he ends up calling Ts, which is the temperature and entropy. And he says that the energy of the system, we already looked at it, we get some value. He said this is equal to some type of exponent. Okay, so this is the energy of the system. And so we looked at the energy of the system, and he said that the probability n defects given n things is approximately, a better way to look at it is through this free energy of the system. And he had drawn a graph like this, where this is the energy of the system. It basically increases exponentially. So this is the energy of the system as the number of defects, right? But if we look at the different chances of its minus Ts, which is related to what we were just calculating here, it kind of follows this trend like this. And so as you introduce, where you see if you were to have too many defects, you have less combinations, or if you don't have enough, you don't have as much. So there is a sweet spot over here. And what we had calculated is the added of these two. So if you were to add this function, which is my negative, to this positive one, the graph would actually look something like this. And so we can see that there is a minimum here of energy. We calculated this to be the n over n equaling this. And so this is the minus Ts term, and this is the E total term, or the E system. And this one is going to be the free energy, which is a combined of them. And what I thought was super neat about this is that you could take this okay, let me see. He basically had it go something like this, where we had calculated this. We basically had approximated this value here. Let me see how we went about it. Let me actually bring up the lecture notes. I'll have to do it sometime later. Basically, what we ended up deriving, though, and I guess I'll try to reverse engineer it. But and I thought this was just incredible. My presentation of it wasn't that great, but this entropy term, we end up deriving out that you get this from. That you end up getting this term out, and this is basically where Boltzmann equation comes from for entropy. I just thought that was the coolest thing ever. I had never seen a presentation, or at least that I could remember that stuck out in my head. And so, if we were to kind of plug this, I guess reverse engineer it back into the whole thing, we actually end up seeing that this, we have our energy of our system, right? Minus TK. So I'm plugging in this to this. TK ln of this. And so if you were to try to I guess reverse engineer this in some way, you could basically say this is this. Okay, how is it? Do you then ln tk oops. Okay, and since these are exponentials, you could basically add them. No. Yeah, I'm gonna have to try to go through this a little bit more in depth on my own, to try to figure out the exact details. But I just thought it was pretty neat the way we had figured this out. Where this basically comes from the number of microstates you have in the system. I really just wanted to do this to try to work out the math, try to follow the process. Um, yeah, I'll have to revisit this once when I make a video of this. It'll probably be a little crisper. These are just the notes I'm taking. And yeah, that's it for this problem. Um, I thought this was pretty neat, especially the way it was presented. Professor Yufan at Michigan. It was a really neat presentation. I feel like I didn't do it justice. But yeah, that's what we have for now with that problem. And if you have any problems with regards to this stuff, I'm more than willing to discuss it. I think this was pretty fun. Um, but yeah, take care and have a good night. Bye bye.